So if I may, I'll start with the Rayleigh Medal. For those of you that don't know, the Rayleigh Medal is the Institute of Acoustics Premier Award, awarded to persons of undoubted renown for outstanding contributions to acoustics. The medal is named after John William Strutt, 3rd Baron of Rayleigh, a very versatile physicist who conducted both experimental and theoretical research in virtually every branch of the subject. A graduate, fellow, and eventually Chancellor of Cambridge University, he was a fellow and president of the Royal Society. His book, The Theory of Sound, remains a landmark text in the development of acoustics. So, Rupert Taylor started working in acoustics in 1964, and in 1968 established his own practice. He has advised private and public sector clients throughout the world in the fields of environmental assessment, industrial noise and vibration, transport noise and vibration, ground-borne noise, ground-borne vibration, construction noise and vibration, community noise, architectural and building acoustics, and noise control in product development. The scope of his work includes writing, at the age of 24, the Pelican book Noise in 1970, which made the subject more accessible to a wider audience. He was also named as an inventor in a number of patents concerning diesel engine noise. Rupert served a term on the Council of the British Acoustical Society and was a founding officer of the Institute of Acoustics as the treasurer during its early difficult financial years, and also a founder member of the Association of Noise Consultants, of which he is latterly the president. He is also a member of the Acoustical Society of America and the International Institute of Acoustics and Vibration, and INCE, the Institute of Noise Control Engineering. He has been unstinting in giving his time to the IOA conferences and workshops, and also his encouragement and enthusiasm for careers in acoustics. As has been mentioned, Rupert Taylor is a world leader in the field of vibroacoustics, of railway structures and tunnels, and was one of the first noise consultants to embrace vibration matters. His find wave system not only permits the prediction of vibration, but using a range of indices, but can also predict sound pressure level and output a WAV file to provide auralization, a facility that is now becoming more commonplace. Rupert is also well known not only for his undoubted technical expertise, but also for his ability to provide a clear explanation of technical matters, and those skills have led to his well-known role as an expert acoustic witness, in which capacity he has appeared in many forums, not only in the courts and public inquiries, but before select committees of both Houses of Parliament. He was for 10 years a member of the Noise Advisory Council, chaired by the Secretary of State for the Environment, and was chairman and deputy chairman of 2 of its working groups. He was a member of the Scots Committee, which drafted the basis of the noise section of the Control of Pollution Act 1974. He has carried out wide-ranging noise research projects for DEFRA, and has also served on a number of peer review working groups. He was also chairman of the working group of the ANC that produced the guidelines on the measurement and assessment of ground-borne noise and vibration, and a member of an ISO working group on vibration standards. Rupert Taylor has worked in all of the major areas of acoustics, but is especially well known for his expertise in the field of vibroacoustics of railway structures and tunnels, in which he is a world leader. In the course of his work on this topic, he developed the time-domain finite difference model, FindWave. In FindWave, a 3D model is constructed of the signal path from the input source, for example, the wheel of a rail vehicle, via its passage through the infrastructure element, rail, mounting, tunnel lining, and surrounding soil, and ultimately to the receiver. The model permits the time-domain vibroacoustic dynamic behavior of a moving train on a bridge or in a tunnel, including all the effects of wheel and rail roughness and dynamic forces to be predicted during the passage of an event. In addition to the mathematical aspect of this system, which is based on theoretical principles, Rupert has also undertaken measurements on completed projects to refine the model's performance, particularly in relation to physical properties used for soil and other elements in the computation process. This combination of wide-ranging experience in acoustics and both theoretical and experimental endeavour makes him a worthy recipient of this particular award. At which point I'd like to present the medal to Rupert. works for you.
My wife is sitting there.
And Rupert will now deliver the Rayleigh address. Thank you.
Thank you very much. Thank you, Mr. President. I will spend the next 30 years trying to live up to this honour, and maybe when I get to the age of 100, like one of my illustrious predecessors, I will merit it. Mention was made of the work that I've been doing in vibration and ground-borne noise, and as you know, this address is about underground acoustics. Most people working in this room are familiar with airborne acoustics and do, from time to time, get involved in vibration, as underground acoustics is really all about. But they will find there are some surprising and complex differences between airborne acoustics and underground acoustics. Here are some of the things which are different. For a start, the source, whatever it is, which might be a machine or a railway or an industrial process or an explosion, it may have up to 6 degrees of freedom. The other thing which is fundamentally different between airborne acoustics and underground acoustics is that there is no unique relationship between amplitude and power. You can't simply multiply things by rho c, and rho c is always the same, and you can flip between sound pressure level and sound intensity level without any difficulty. That can't be done with vibration, because impedances vary enormously, as I'll be explaining. The other thing in airborne acoustics is you can usually forget about the near field. You're nearly always working in the far field, and you get neat relationships like inverse square laws, and the computations are quite simple. In underground acoustics, where wave speeds can be very high, they can also be very low, but they can be very high, the near field can be dimensionally large and extend over areas where you are doing measurements, where you're doing predictions, and if you don't take account of that, you'll get very large errors, and people do. In airborne acoustics, we treat air as pretty much linear. If you look at derivations of the airborne wave equation, lots of simplifications are made, including the fact that air is a linear behaving medium. That does not always happen in vibration, and whether it's materials such as vibration isolation polymers, they can stiffen up with increased deflections, or if it's the soil at the bottom of the seabed and the legs of an oil rig being moved under wave action, the amplitudes can be large enough to produce non-linear responses in the medium concerned. That's just part of it. Once you start to move away from the source, propagate towards the receiver, waves can propagate in 10 or even more different ways. There are at least 10 different wave types in an elastic medium. It's the elastic bit that really makes the difference. And when you're describing the waves, you can choose 4 or even more descriptors of their amplitude. When you start to look at the way the waves decay with distance from the source, they do that in at least 4 different ways. And there are lots of different paths by which waves can propagate from source to receiver. The shortest one is by no means the one of greatest interest, and detecting which one is the one to be concerned about, to measure and to predict is quite a challenge. And just to make things that bit more difficult, we certainly can talk about source, path, and receiver, but in vibration they are coupled one to another. The path affects the source affects the path affects the receiver, and vice versa. I mentioned the fact that we don't have the convenience of multiplying things by rho c all the time, but we do have the fundamental analogies that you do in airborne acoustics, power being equal to the time average of the product of force and velocity, or the time average of velocity squared times the impedance. And certainly if you do have a very large space full of the same material, like clay, for example, you do get an analogy to the rho c of airborne acoustics. We tend to deal in force rather than pressure, so we talk about impedance as force divided by velocity, or its reciprocal being mobility. I talked about the number of different ways that waves are transmitted. Here are most of them. The compression wave is most similar to airborne sound pressure, but you'll only find it in a huge homogeneous isotropic area of something like rock or clay, where the source is a buried pressure source, such as an explosion in a small cavity down in this medium. We have other waves, details of which I'll show you in a minute. Head waves, which are rather curious. Of course, we get shear waves, which most people are familiar with. They are polarized. They can be at any orientation. In seismology, they're divided into horizontal and vertical ones called SH and SV. You've heard the name Rayleigh, and the Rayleigh wave most people are familiar with as a surface wave with very interesting characteristics, which I'll talk more about. We don't actually have Rayleigh waves on this planet because they are waves at the interface between an elastic half space and a vacuum. We always have, except in laboratory circumstances, a fluid above the vacuum, above the half space, and those are actually called Scholte waves if you have an elastic half space and a fluid medium, which may include a liquid medium. Actually, the Scholte wave was developed in the context of seabed vibration propagation. Lamb waves are surface waves as well, but you have Lamb waves when there are two surfaces, as in a plate. Love waves sound good. They are laterally displaced shear waves on a surface. Stoneleigh waves are like Scholte waves, except instead of being an interface between an elastic half space and a fluid medium, they're an interface between two different kinds of elastic half spaces. And BO slow waves are interesting. I'll talk a little bit more about them. Maurice BO, along with a co-worker called Stoll, solved some equations for the propagation of waves in a liquid-filled and also just a fluid-filled porous elastic medium. And as well as getting variations on the P wave, the compression wave, and the shear wave, which give very similar results to the same waves in isotropic media, he also found that you get the appearance of a thing he called a dilatational wave of the second kind, and it has very interesting characteristics, which we'll come back to. Those are all the waveforms I can think of for propagation in unbounded elastic media. In structures, they manifest themselves in additional ways. You get torsional waves in bars and columns, and bending waves, of course. In cylinders, you get helical waves propagating along them. And you, of course, get longitudinal waves traveling along bars and columns as compression waves. When you set about measuring them, there are lots of things you can measure. Acceleration's easy to measure because accelerometers are widely available, as are geophones, which measure velocity directly. Technically, you can measure displacement. You would do it with a strain gauge if you were going to do that, and you can use that indirectly to measure force. Those are all vector quantities and need to be measured in 3 axes. You do occasionally see the scalar quantity of pressure measured, sometimes in downhole tests with borehole experiments to measure ground conditions. Sometimes you fill a borehole with water and lower a hydrophone down it, in which case you're measuring the scalar pressure quantity. I also mentioned these different rates of attenuation with geometric spreading. We do have something analogous to the inverse square law. That's the 1 over r, 6 dB per doubling. We're always in the 20 log world in vibration, almost never in the 10 log world. We're not squaring things because we can't do that neat swapping of intensity and pressure. So that's why 1 over r, not 1 over r squared, is 6 dB per doubling. But in fact, if you have compression and shear waves from point sources on the surface of a half space, it's 1 over r squared, that's 12 dB per doubling. And if you then have compression and shear waves, if you have Rayleigh waves from point sources on the surface, it's 1 over root r. And the interesting one is if you do have, and they're a little bit rare because it's more theoretical than actual, a line source producing Rayleigh waves on the surface, there is no loss due to geometric spreading. The distance law is 1. I talked about the fact that the near field in an elastic medium can be quite large and can be quite important, and if you neglect it, you can get things wrong. Now, I need to explain what's going on here. This is talking about a small spherical source in an elastic medium, very deeply embedded in isotropic clay, for example. And whereas in airborne acoustics, you can more or less ignore the fairly interesting thing that happens in the near field of a spherical airborne source, with the classical thing of a point pulsating sphere that's in the first few pages of most acoustics textbooks. Our equivalent of the pulsating sphere when you're underground in an elastic medium behaves in a very interesting manner, and it's all dependent on this thing called Poisson's ratio. I've already talked about shear waves and compression waves, and those, as I will show in a minute, are dependent on 2 different modulus values for soil, a constrained modulus and a shear modulus, and the 2 are related to each other through Poisson's ratio, which is actually, if you have a bar and you squash it, it's a measure of how much it bulges or contracts when you stretch the bar. And if the Poisson's ratio is below 1/3, which it is for some media, then it's all fairly boring, and the effect is that the reactance part of the radiation impedance of this buried sphere is stiffness-like at all frequencies. But if the Poisson's ratio goes above 1/3, we start to get a resonance effect in the radiation impedance of this sphere. What happens is that as the Poisson's ratio rises from 1/3 to its maximum allowable value, it cannot exceed 1/2, this resonance frequency appears, which is the point in the frequency spectrum where the reactance part of the radiation impedance switches over from being spring-like to being mass-like. And just with any resonance, there is a point where that the reactance becomes 0, and you get a resonant effect around the source. As the Poisson's ratio gets quite big, and it will get quite big with fluid saturated porous medium, and I need the pointer if anyone's got it. Thank you very much. It can reach in sand saturated with water. Poisson's ratio can get quite close to 0.5, Life gets very interesting when that happens because, in theory, the ratio between the compressive, the constrained modulus, and the shear modulus can become infinite. It doesn't in reality because you never actually get real properties that would cause that. But nevertheless, if you had a medium with a Poisson's ratio of getting on for a half, you get a very pronounced resonance effect in the radiation impedance. What this is actually showing is the mobility. So it's the ratio of velocity to force. And when we get this big peak in the medium with a high Poisson's ratio, what it's actually saying is around this frequency, and in a half space of Clay, the frequency is in an area of some interest. That's 1,000 hertz, that's 100. So this is sort of tens of hertz. The velocity for any particular force in the medium rises up by as much as 10 dB. And the reason that I draw attention to this is you can see geotechnical experts go out and try to do measurements of the properties of the soil with, say, 3 boreholes. They put an impulse source in one borehole, which might be an electric spark. They have another borehole nearby, which might be a case of the sort that I mentioned where you fill it with water and put a hydrophone in it, measure the signal at that intermediate borehole and call that sort of quasi-source, and then measure at a third borehole some considerable number of meters away to try and measure propagation through the soil, work out the shear and the compressive modulus, and also try to work out the loss factor. But if you don't consider whether you're operating in one of these areas, you can find that if you're measuring velocity with some of your transducers, pressure with the others, there can be a huge departure from the simple case in terms of the relationship between the two. And you can get completely false attenuation measurements between the second borehole and the third borehole, when in fact what's happening is solely geometrical and not anything to do with losses. And I'll come on to losses. There are different ways in which vibration is attenuated through the soil apart from the geometric spreading, which I've been talking about. And they can be due to viscosity, they can be due to hysteresis or friction. And across the frequency range of interest for most of us, the loss factor is not frequency dependent. That doesn't mean to say it doesn't change, that the attenuation doesn't change with frequency, but the intrinsic loss factor of the medium tends to be independent of frequency. But if you dig down into the reasons, the mathematical reasons for there being viscous, hysteretic, or friction losses, you'll be really hard pressed to find loss factors more than about 0.05, even though there are some widely referred to handbooks out there that talk about loss factors of much bigger numbers than that, even as much as 0.5. But the reason is that a lot of the excess attenuation in propagation through soil that is not explicable by geometric effects is due to other things: scattering, refraction, and wave conversion. Now, that loss factor I was talking about, eta, is best understood as the imaginary part of a complex value assigned to the 2 moduli that I mentioned. The constrained modulus is the one that determines the speed of P waves, the shear modulus, obviously shear waves. But take great care, because there are other moduli which you see in information which are not what you think they are. Don't confuse constrained modulus with bulk modulus, because they are different. And when you're looking at geotechnical reports, it's extremely hard to find the information in the right form. And critically, max means you're measuring these at infinitesimally small strains, because the behavior of soils, less so rocks, changes dramatically as the strain increases, and most civil engineers are interested in properties of soils at much greater strains than we are when we're thinking about vibration. And the best place to go to read all about it is a recently published ISO technical specification. It's not a standard, it's the second, despite the fact it's got part 32 after it, it's the second part published of ISO 14883 7, which is the general guide to vibration from railways, effectively. And it is a very good discourse on the matter of measurement of dynamic properties of the ground. And you'll find in there how to sort your constrained modulus from your bulk modulus and all the rest of it. Now this BO slow wave, the dilatational wave of the second kind, this is a plot actually generated digitally, numerically, using the find wave method that the President kindly referred to in the citation. And it shows that if you have a source in a fluid-filled porous medium, as well as the normal compression wave, which will propagate away through the medium, you also get this slow wave. And the reason it seems to be higher frequency is simply because it is slow and therefore its wavelength is very short. And the consequence is that it attenuates very rapidly. You might look at the work, you can find BO, the papers of BO and BO Stoll in JASA, and they make very interesting reading. And you might think it's just one of those interesting things about elastic waves that I don't really need to worry about. But if you think about the case that you do encounter, which is waves traveling from a saturated porous medium to a dry one, or a less saturated one, or vice versa, this is what happens. You arrive at an interface between a dry and a saturated region of the medium, and a BO slow wave appears, is rapidly attenuated, and that actually gets rid of some of the energy without there being any, not involving the loss factor, not involving geometric spreading. It's just the conversion of one form of wave to another, with the result that there is much greater attenuation in one of the other waves that is created. Same sort of thing happens to a smaller extent with reflections from interfaces between one layer and another. If a pressure wave arrives at an angle at an interface between a fairly hard region of elastic soil space, so to speak, and is reflected, what you get is not just a reflected P wave, but a reflected P wave and a reflected shear wave. And as all shear waves have slower wave speeds than P waves, the attenuation is much greater. So the wave conversion leads to greater attenuation through the existence of another wave type. As far as attenuation due to the loss factor part of it is concerned, you can actually simplify it quite neatly, where I showed you complex moduli as 1 plus j eta I eta, eta being the loss factor. You can actually boil it down to an attenuation due to damping of 27 times eta dB per wavelength. That takes into account the fact that you get more attenuation with increased frequency because the wavelengths are frequency dependent. But it's quite a useful mnemonic. If you're given a loss factor, you don't have to go through many punches on the Excel spreadsheet. It's just 27 times eta dB per wavelength. Now I'm going to show you some examples of some of the waves that I've been describing, done using the finite difference method, using the find wave package. Finite difference involves just discretizing space on an orthogonal grid and alternately computing the state of each point on the grid according to the strain, the modulus properties of the medium, and repetitively recomputes velocity and displacement over tiny time steps, and millions of them per second in some cases. And the first thing I'm going to show you is just an animation of some of the wave types that we've been discussing. This is the consequence of a vertical impulse on the top of a half space. So, the condition that Rayleigh assumed when addressing the Rayleigh wave phenomenon. And what you see there is several of the waves that I've been describing appearing. The larger one was the compression wave. It's the fastest, so it travels the furthest, and it's actually quite simple, except the next slide will show a repeat of this under slightly different circumstances. If you look closely at the next slide, you'll see manifestation of one of the things I mentioned, which is that whereas we've got 1 over r geometric spreading in an infinite half space, on the surface of a half space it becomes 1 over r squared. So there is some geometric damping at the top of the half space, and you'll see the P wave squeezing down at the top. It's quite interesting. This, of course, is the shear wave, and we'll see in better detail on the next slide. It turns itself into a Rayleigh wave on the surface. But the intriguing one is here, I hope you can see it, we'll see it repeated in a moment, is my friend the head wave. I didn't actually know anything about the head wave till quite recently when I was looking at numerical modelling done by Catholic University of Leuven, who do this kind of modelling, and there I saw this head wave, and I thought, well, that's intriguing. If find wave is any use, it must be capable of predicting a head wave. Sure enough, it does. What it is simply two other waves. It's a P wave going in one direction and an S wave going in another direction, and it's effectively the consequence of a P wave going out along the surface and doing the effect that you get throughout acoustics of Huygens' method of wave construction, where you can treat any point on a wave front as a little source in its own right. So all the little sources which are created by the passage of the P wave out along the surface propagate down into the medium, but they will do so at shear wave speed. So you get a wave front, which is the locus of the extent of each of these little shear waves. Now the next slide shows the same thing again, but I'm going to show you the fluid space above the half space. In other words, we're leaving Rayleigh behind, we're into Scholte waves now. Same thing, because if the fluid is not a liquid, which is what Scholte was interested in, if the fluid is air, then Rayleigh waves are Scholte waves. We don't really need to split hairs. But just watch this one carefully. There was the head wave. There's the shear wave. There's the Rayleigh wave. And the thing which is intriguing is we've also got a head wave in the fluid above the half space. It only occurs if the Rayleigh wave speed is greater than the speed of sound in air, which it can be. And the consequence is that if you're on the surface of a homogeneous half space, an area where the ground is pretty much clay all the way down for dozens of meters, and somebody hits the ground with a hammer, such as a pile driver, you can actually hear the airborne sound more than once, because as well as the conventional P wave coming through the air, you'll also get a wave radiated off the surface of the ground as a secondary source. Now the next one is going to be the same source on the same half space, but with a layer of a different elastic medium below the surface. These models are all about clay, but there's going to be a layer of limestone just below the surface, and you can see the wave being reflected off it. It's just an illustration of the effect of layering. But the final one of this type of slide is going to show you something which is quite important and easily forgotten and is very practical to those of you who go out and measure vibration in free field, and that is that the arrival of a wave at the surface of a half space actually results in velocity doubling at the half space. So if you've done lots of lovely calculations of the propagation of vibration through an unbounded elastic medium, and you use that to say to somebody what you predict the vibration is going to be on the surface of the ground, don't forget that if the surface is above the source, double it. You watch carefully there. Do you see it reflected from the surface? And you get a doubling at that point. Now, we've been enjoying the luxury of a homogeneous isotropic half space, but they don't exist in reality, and we have to take account of the fact that soil properties vary significantly with depth. Rock properties vary according to whether it's fresh rock or whether it's weathered, slightly weathered, highly weathered. And to do any sort of modeling of propagation of vibration through the ground, you've got to know how the properties of the soil or the rock vary with depth. You can do things by measuring the downhole, cross-borehole measurements that I've been talking about, but you can also invoke one of the interesting properties of Rayleigh waves. Perhaps I should be calling them Scholte waves, but I don't want to be rude to the gentleman whose medal I've just been given. In that Rayleigh waves are deeper at longer wavelengths. They're basically surface waves, but they do have a tail which extends down into the ground, and the lower the frequency, the deeper that tail. And in almost all actual ground conditions, the deeper you go, the higher is the constrained modulus, which means that Rayleigh waves in that kind of environment become dispersive. In other words, their phase propagation speed is frequency dependent, which is not the case of a pure Rayleigh wave or pure Scholte wave. They are non-dispersive, but in a real life ground surface where the modulus increases with depth, they are dispersive, and you can use that to set out an array of geophones, create an impulsive source and measure phase angles at successive distances from the source, and you can actually recreate, synthesize a picture of what the subsurface conditions are like in terms of wave speed. You can't detect from that what the other properties of the soil are, such as its bulk density. You have to use other means of determining that. But you can get really quite elaborate pictures of what's below the surface using a thing called surface wave, multi-channel analysis of surface waves. And that's just an example of what you can measure from this sort of approach. And this is a plot of what the conclusions are, that down to sort of 12 to 14 meters, or something like 1,400 meters per second. Then as you get further down, 2,500 towards 3,000 meters per second, and then there's obviously another kind of geology down there. You get well up into the 3,200s, and it's probably the most usable way of determining what's going on underneath the surface of the soil. What I'm now going to do is show you what happens if you put all this into a three-dimensional numerical model. It's the finite difference approach that I've been describing. And to illustrate what you get, I'm going to show you the results of a model of a building on piled foundations over a railway tunnel in a case where it's mostly clay, but there are some layers of gravel and made ground and alluvium. That's the model. It's a building, pile foundations, concrete pile caps. The ground floor is a concrete slab, but just to make life interesting, the upper floors are cross-laminated timber, which has obviously completely different properties from concrete slabs. And we'll have a look just to see how different are the results and what we can learn from it. There's a section through the model that we're going to look at, and the next slide is going to be a speeded up plot of something quite curious. It's going to be power flow, but it's done by multiplying the pressure signal, the force signal with the velocity signal at each point in the matrix of cells. That actually gives you a slightly odd result, because you may know if you multiply two sine waves together, you actually double the frequency. And that's why I was at pains to say earlier on that we were looking at the time average of the product of force and velocity to get impedance. But you can see, you get the best view of what is happening if you do plot this power term, starting with the vibration of a train running in this tunnel, exciting the soil, getting itself involved with the piles, propagating up the building, vibrating the floors, and radiating into the spaces above the floors. And you can see that whereas the piles play a part, they're by no means the most important thing that is taking the vibration from the tunnel up into the building. It goes without saying, the behavior of the whole system is extremely complex. I mentioned that we were looking at basically clay, but there's a layer of, I said limestone, actually there's a layer of gravel in there and then more clay above it. And the question does arise, in practice, how much effect do you get when the ground is layered compared with when you've got an isotropic half space? The effect is quite significant. There is a comparison between two models run, one with isotropic homogeneous soil and the other with quite significant layering. It's the spiky blue one that is the layering, and that is actually taken from the lithology of Copenhagen, where there are varying hardnesses of chalk laid one upon the other, and then weathered chalk and till or overburden on top of them. But now we're looking at what happens when this vibration arrives at a building, and one of the things that gives people a lot of grief when they're trying to do predictions of vibration transmission into buildings is something called the coupling loss factor. In fact, it's quite hard to find any information about coupling loss factor. That there is some data going right back to the UMTA handbook in the 1970s showing what happens between the ground and one kind of building or another. The first thing to do is be absolutely clear what you're looking for. Are you looking for the difference between vibration in a virgin, undeveloped surface of a half space, the ground where there's been no building before, and what you'll get in the foundations of a building that's about to be built on that surface? Or are you looking at the difference between vibration in the surface beside a building and vibration in its foundations? And it does make a difference which is the thing you're looking for. There's a little bit of help to be found in the literature, because from the seismology end of things, it is well known that a plate on top of a half space behaves as if a large amount of the soil in the half space is actually attached to the plate. And the plate, even though it might be massless, or just a thin, light metal plate, behaves as if it has quite a large mass due to the fact that a considerable area of the soil it's sitting on behaves as if it's attached to the plate. As with most things in vibration, the algebraic solutions are pretty much intractable. But in the case of a disk on an isotropic half space, there is a closed form solution, and it's quite interesting. Here is a plot of the coupling loss factor, and it's for a circular base with an average radius of 18 meters and a load of 150 meganewtons. So it's sort of building-like. But on the other hand, it is the highly theoretical case of just a disk on an isotropic homogeneous half space. The scale isn't very clear, but what it's showing you is that this is minus 20 dB, it's minus 15, minus 10, minus 5, and then you get amplification around the natural frequency of that mass of the soil that's attached to the disk on the spring-like behavior of the rest of the soil underneath it. And above that frequency, you get this fall-off in the response of that disk to excitation from vibration coming up through the soil. And those of you who've done work trying to look up coupling loss factors will recognize the shape of that curve, and you'll now get some understanding of why it happens. In that model we looked at a moment ago, the coupling loss factor was like this. And sorry, the scale doesn't show as well as I would have liked, but you get, again, small amplification at low frequencies, and then about 5 to 10 dB across the middle of the range. partly due to the same effect as the disc on the half space, but of course in this case the building also has its piled foundations that we need to take into account. Now we got as far as getting the vibration into the building, and we might know exactly what vibration we have in the floor of a room in the building, but we've got to convert that into a sound level in the building if we're interested in one of the main reasons for doing all this, and that is not so much vibration for its own sake, but vibration from the point of view of its capacity to re-radiate sound as ground-borne noise, as re-radiated or structure-borne sound. In other words, what you get in a room when the floor vibrates behaves as a loudspeaker and creates a sound field in the room. The first thing to bear in mind is that we're dealing in low frequencies, long wavelengths. We're only ever working in low mode numbers as far as the behavior of the structures are concerned. And if we take a fairly simple case, which is a rectangular floor plate, and make the assumption that it's simply supported at the edges, these are what the mode shapes look like. There is a mode 0, 0, which would be if the whole building was being pumped up and down as a piston. There's mode 1, 1, mode 1, 2, mode 2, 2, mode 2, 3. Those actually, you don't actually have to go much higher than that to cover the range of frequencies that we're usually dealing with if, for example, what we're faced with is a rumble from a train in a tunnel underneath the building. Now let's look at the equivalent mode shapes in the airspace in the room. These are three-dimensional, of course. The plate mode shapes were two-dimensional. But mode 1, 1, mode 1, 2, 2, 2, 2, 3, utterly different. They have their antinodes in the corners. They have almost the opposite shape to the mode shapes of the floor. And you can see at a glance that the question of how much of the vibration of the blue is going to excite the modes of how much the vibration of the red is going to excite the modes of the blue, in other words, the air in the room. You can look at it another way. You can plot those very same plots, but using a log scale, in other words, a decibel scale, and compare them like that. And again, it's going to be non-trivial to work out how much vibration in the floor with a mode shape like that is going to result in a sound pressure level in the room with a mode shape like that. If you make the assumption that the room is nearly lossless, in other words, a very, very long reverberation time, you get a very peaky response. But what this is actually telling you, what is plotted here, is LV minus LP, and for a very long reverberation time. In other words, if you express vibration velocity as decibels re 1 nanometer per second, 10 to the minus 9 meters per second, and express sound pressure level as the usual, decibels re 20 micropascals, what's the difference between the two? Some of you who've wrestled with this a bit will know that it's quite common to say the difference is 27 because of a paper by Kurzweil some time ago, which reviewed various workers' conclusions and thought that was a reasonable estimate to make. And indeed, at higher frequencies, it is sort of minus 20-ish, but it dips right down to nearly minus 40 at some of these anti-resonances and can go up to almost 0 at resonant frequencies in the room. We move into the real world with a room that has a finite reverberation time, come way back from approaching infinity. And this is for half a second in a room 3.5 meters by 4 meters by 3 meters high, but it is still a very lumpy curve indeed. We have still got these anti-resonances down here, and again got some resonant peaks, and up here we're only about sort of minus 15, something like that. And it makes you wonder, what on earth should we do? Is that figure of 27 any use at all, or do we need to tear it all up and do some other approach? You can simplify it a little bit by moving from narrowband frequency analyses into third octave bands, and you get curves looking like this for different room shapes. Same characteristic of there being an anti-resonance towards low frequencies and a much smaller difference between LV and LP than 27. So another of these models will throw a little bit of light on it. This is, again, a railway tunnel with different layers of soil on top of it, and a simplified building on the top. It's got a ground floor slab of concrete and a first floor slab of timber boards on joists. And after you've run the model, you can see that at ground floor, the vibration modes of the floor, you can see mode 1.1 there. And again, you can see mode 1.2 appearing at first floor. You can see that characteristic node in the middle and the highest amplitudes in the corners. But at first floor, where it's timber boards on timber joists, you can see we're up into mode 1.2 rather than mode 1.1. And again, we've moved up a mode group in the airborne sound mode shape. You can then go one further and go to a really complicated building, which is not simply rectangular, got all sorts of different shapes of rooms and floor layouts. And what we've got here is a plot of floor vibration in terms of vertical velocity, and this is a plot of airborne sound level in the spaces above the floor. And they're done in such a way that if LV minus LP were to equal 27, then the colors would match, if you see what I mean. And it's quite interesting to see the colors, if you stand back from it, the colors aren't a bad match. And LV minus LP of 27 doesn't take you into the wrong ballpark. But if you were to go to a specific location like that one where it's green, that is at ground floor level, and that's vibration, and you go to the ground floor level airborne sound level, it's way up in the yellow and orange. So at any specific location, you can get huge errors from making a broad assumption about what the difference between velocity and pressure is. These are spectra of the same thing, and at ground floor level, where there's a concrete floor, the two pairs of curves are one for the LV minus 27 and the other is for LP, and they overlay each other reasonably well at an assumption that the difference is 27. But on the first floor, where it's timber boards on joists, there is a huge difference. Now, suppose that huge difference was such that we wanted to isolate the building on bearings. We often fall into the trap of thinking it's a single degree of freedom system. We can look up in the vibration pages of our handbooks what happens with a lump on a spring, how much reduction you get according to the static displacement or the dynamic stiffness of the spring, and you come up with nice large numbers. But of course, real buildings are complex dynamic systems, and some of the most interesting buildings that people are currently contemplating putting on springs are multi-storied, 40 floors or something like that. And one of the intriguing things that happens in those cases is if you take the floor as a mass and the columns supporting it as a spring, and we will find that the circumstances are such that even if they're just concrete columns or steel I-beam columns, their own compressive stiffness becomes such that they do behave as springs. What happens is actually quite interesting. If you're up on the 9th floor of this building and you calculate the mass of the floor on the spring-like behavior of the columns, you'll get a natural frequency out of the system. If you move down to the 8th floor, you've got 2 floors, 2 sets of springs, and as in all vibration cases with multiple degrees of freedom, you get 2 coupled frequencies, neither of which is the same as the original one. Move down floor by floor by floor, each floor introduces a new coupled frequency, and you end up with the lowest of these coupled frequencies once you get down to ground floor at really quite a low frequency. And if you take this hypothetical building, you see that the lowest frequency, which is the lowest of the coupled frequencies caused by all the floors and all the springs from the columns supporting them, is something like 7 hertz. Now, this arose when somebody said to me, I've got a building like this, I need some isolation from vibration coming up from the ground. I'm thinking of putting it on something like 7 hertz bearings, but what's the point? Because the natural frequency of the building on its columns is 7 hertz. There is some point, because if you treat this what these calculations are is treating the system as a transmission line, which anyone who's done electrical power transmission calculations will know about. If you insert 7 Hertz bearings underneath a building, multi-story building, which has its own lowest coupled frequency around 7, you still get attenuation. Nothing like as big as you get from a single degree of freedom system, but it is still there. So what have I achieved? I think I've convinced you that apart from the similarities and dissimilarities between airborne and underground acoustics, there is much more you have to know before you can get anywhere with interpreting measurements or applying them to predictions. Many of the parameters you have to know are extremely difficult to know and to discover and to measure. And really, the conclusion that we reach is that as much effort needs to be devoted to estimating the magnitude of the uncertainty as to measuring and predicting the results themselves. And there's a lot of physics to be understood to help to minimize the uncertainty. And with that, I will conclude, Mr. President.
Are there any questions?
Yes, the BO slow wave. As you say, it's an interesting wave, but most building acousticians know about it already, because it's the wave that's responsible for the properties of sound-absorbing materials, air-filled.
That is a very intriguing thought, and I will consider it further.
Any other questions?
From all of the geometrical distribution of the vibration amplitude that you've just talked about, would you say that when you're doing vibration survey for designing a building, that your resolution between surveyed points needs to be a lot closer together to get a more accurate idea of the vibration environment that you're going to build on?
Without any doubt whatsoever. The first stage is even simpler than that, to take very great care in understanding and recording precisely where you have measured and in understanding the structure beneath the point where you attach the transducer. But ideally, as you'll have seen from some of the plots I've shown, you would need to have a really fine resolution grid of measurements to remove hefty uncertainty. So yes, you are right.
Do you think there's a trade-off between practicality and knowing enough to design the building?
A trade-off between what, sorry?
The practicality of actually doing the measurements and getting enough information to properly design the building?
I think the practicality of it is because it is not reasonable to have the huge array of measurements that you really would like, is to be able to understand better the nature of the structure you're measuring on, to make a pretty good job of understanding where the maxima are going to be and where the minima are going to be, and try and find them. But if you think about it too much, you will actually lose the will to live and give up the work altogether.
Okay, in the interest of time, maybe if you've got any other questions.